This is a short video about the Legendre symbol, some more. Video 2 about the Legendre symbol, I should say, from Stein's book on elementary number theory. And just to remind you, we talked about the Legendre symbol in the last one, and what does it do? It is the symbol that represents whether or not a given integer a is a square mod p. So in other words, does a occur as x squared, where x is some number, 1 through p minus 1, say. If it is, then the Legendre symbol would be 1. So if a is a square mod p, which means a is a quadratic residue, there's a lot of vocabulary in this section. So if a is a square mod p, then the Legendre symbol comes out to be 1. And if a is not a square mod p, in other words, it's a quadratic non-residue, then the Legendre symbol should come out to be -1. And if like p divides a, in that case then we'll say the Legendre symbol is 0. So again, what this is it's just like a quick tool that is supposed to capture the idea that a is a square mod p, yes or no. 1 if it is, -1 if it's not. And what we're interested in doing is what are some tricks that I could do to say compute the Legendre symbol? So maybe right now, like to answer the question, is a square mod p? What you've got to do is you've got to just square, all the elements mod p and figure out, well, do I get a in that list? And that seems a little bit inefficient. Maybe there are some tricks that I can do with this Legendre symbol. What kind of rules does it satisfy? What kind of algebra can I do with it? And that's what this video is about. So what we're going to get into is a concept from a modern algebra class about a group homomorphism. And so what a homomorphism is between two groups is think of it as a function. A lot of times we say map between two groups, G and H, such that, so what makes it a homomorphism is the following property. This function has this very special property. Phi of a product, a times b, should split as phi of a times phi of b. And the way that you should think about that is, if you remember about groups or sets that have some kind of an operation on them, say like addition or maybe like multiplication. Anyway, pick one operation. The operation has to satisfy certain things, such as there has to be like an inverse, a way to undo the operation. There should be like some kind of an identity, and some other things like associativity as well. So G and H, they both have their own operation. Think about that for right now. What this function between G and H says, or to be a homomorphism, this function between G and H has to respect the operations in both sets. And in notation, that's what I've highlighted here. Phi of whatever the operation between two elements in G is should be the operation in H of the outputs on A and B respectively. So phi should split in that way. And recall that we'd say a function's surjective, if it's onto. In other words, for every C in the codomain, there is some A in the domain where C is the output of A. So why is this useful for us? Because what we're going to see is that the Legendre symbol is actually a group homomorphism, and I'll show you how that's useful. But first of all, let's just kind of talk through the proof really quick. So if I take this map psi, so psi is going to be my group homomorphism between the group of units mod p. So remember, that's a group whose operation is multiplication. Since p is a prime, I know the elements of this thing are just the numbers 1 through p minus 1. To the set plus or minus 1. That's a group that has two elements, 1 and -1, and the operation is multiplication. So if you think about it, if you square -1, you get 1. So you just land back in the set. And of course, if you square 1, you get 1. But what I'm saying is, if you were to multiply 1 and -1, you're going to get one of those numbers back. So it's closed into the operation. So what does this map psi do? You plug something in from 1 to p minus 1, it ought to spit out a number 1 or -1. And how? Well, psi of a is going to be the Legendre symbol of a mod p. Turns out that this is a group homomorphism. Moreover, it's surjective, which maybe isn't too hard to believe. If there's only two things in the codomain, it's pretty believable that each of these guys are going to cover those two. They're going to hit those two. So what is the proof of this? Just to talk about it quickly, remember Z mod PZ star is a pretty nice group in that it's cyclic, or another way to think about that, we talked in a few videos ago about primitive roots or primitive elements. And so in Z mod PZ star, because P is prime, you've got a primitive element. We'll call it G, and the point is that G generates this group. If I start taking powers of G, I recover all the elements in Z mod PZ star. And the way we're going to write that down is right here. I've got G, I've got G squared, I've got G to the P minus 1 over 2. By the way, we're still assuming that P is an odd prime, so P minus 1 is even, therefore it makes sense to divide P minus 1 by 2. and I compute all these powers, and what do I know? I know from Euler's theorem, or another way to think about that is from Fermat's little theorem, is that g to the p minus 1 power should give me back 1 mod p. So what am I trying to say? In this list of all these powers of g here, I do recover all the elements of z mod p z star. They're all represented as powers of g. Now, like we said, p minus 1 is even, so well, what are the squares of elements in this group? They should just be all the g's that have even powers on them. And what we want to look at here, I mean, we could do that algebra, right? The 2's simplify, so you just get g to the p minus 1, which is 1. Whoop, that explains this part right here. But then in the next one, right, what's the next even power? It would be g to the p plus 1. And what we claim is that equals g squared. And if you think about it, g to the p plus 1, what should that be? Equal to maybe g to the p plus 1 over 2 squared. That's how I get g to the p plus 1. And what would that be, of course? So what are we doing? I'm saying we're squaring this to get this. And if I simplify that, okay, yeah, g to the p plus 1. And how can I rewrite that? Well, that's g to the p minus 1 times g squared if I think about, exponent rules that we know and love. Why is that cool? G to the p minus 1 is 1, according to Euler's theorem. Therefore, we get g squared. So if that clears up what I've highlighted in blue. Yes, g to the p plus 1 should be g squared. And then this very last one down here, g to the 2p minus 1, that's what you get if you square this equation right here. So I'll kind of undo some of this so you see what I'm referring to. If you square what's circled in purple now, you should get 1. So g to the 2p minus 1, that should be 1. So what's the point then? My point is that I see from this point onward, from here, the list just repeats itself, right? So these are, what are? So in this case, the perfect squares are just the powers of g that have an even exponent, right? An even n as an exponent. So where are we at as far as the proof goes? All the perfect squares in z mod p z star are exactly the powers of g to the n, where n is an even number. And what are the odd squares then? Well, the odd squares are the in-betweens. And well, what's in between the g's that have even powers? Of course, it's the g's that have odd powers. So the non-squares mod p would be the powers g to the n, such that n is an odd number. So I hope that makes sense so far. And why is that good? That is going to allow me to finish that psi is a homomorphism. And so, well, why? In that case, maybe we could do one of these, talk about what's going on. So in this case, okay, an odd plus an odd is even. It's not very deep, but let's see why is that good. So what have I got? I'm going to apply psi to an odd power of g. So I'll do 2 to the m plus 1 times g to the 2 to the m plus 1. So that's an odd times an odd. And so what do? This says an odd plus an odd. Well, if I simplify inside of that, well, I do use exponent rules where I add the exponents. So that's where odd plus an odd's coming into play. 2 to the m plus 1 plus 2 to the m plus 1. And if I simplify some more, I see that that's g to the 2 times m plus n plus 1. So why is that cool? Because this is g to an even power. And if I look back, well, wait a minute, the perfect squares in z mod p z star are exactly the g's that have even powers. So what do I know? What does a psi do? Psi spits out the Legendre symbol of this number. If that's a perfect square, its Legendre symbol is 1. So this is equal to 1. Now, what does this have to do with being a group homomorphism? What we're going to check now is that is this the same thing as if I applied psi to each of these powers of g separately? And if it's a group homomorphism, then they have to be the same. So maybe I'll put a little question mark over here. Is that the same thing as psi? I can't draw psi. What's going on with my life? Here we go, psi. G to the 2m plus 1 times g to the 2m plus 1. What if I apply, I just have a 2m plus 1 there, don't I? G to the 2m plus 1. So what if I apply psi to each of these two elements separately? I need to make sure I get 1 in order to say this is a group homomorphism. So let's do that. So, well, wait a minute. This is psi of an odd power of g. And what do I know? I know that the non-squares are exactly the odd powers of g. So psi of that, what does psi do again? Psi is the Legendre symbol of that. So it's a non-square mod p, therefore its Legendre symbol is minus 1. Same logic, g to the 2m plus 1's Legendre symbol is minus 1. When I multiply these two, yes, I get 1. So we've just verified in that instance that the Legendre symbol can split. into those two pieces. And the rest of the proof is pretty similar. It follows that exact same logic here because of these nice facts about evens and odds and what happens when you multiply them or add them together rather. So why is that useful to us? I'll show you an example in a moment maybe. Actually, I'll just show you now. So if I wanted to do something like figure out what's the Legendre symbol of something like, I'll write it this way. How about 12 over, I don't know, 17, say. So remember the question is here, what am I asking when I'm thinking about this Legendre symbol? Is 12 a square mod 17? So what I could do now is I could think about, well, how does 12 factor? Well, 12 is 3 times 4. So this would be 3 times 4 over 17. Because we just proved that the Legendre symbol acts like a homomorphism, that means I can split this. The Legendre symbol of 3 times 4 over 17 has to be the same thing as the product of the Legendre symbol of 3 mod 17 and the product of 4 mod 17. That's that homomorphism property with this equality right here. Now I can even say more. I know that 4 is 2 squared. So what I'm going to do is I'm going to apply the homomorphism property again, which tells me that if you think about it, I should be able to write this as 2 over 17 times the Legendre symbol of 2 over 17 again. Maybe another way that I'll write it though, just to emphasize, you could say that same thing with powers. This should be the Legendre symbol of 3 over 17 times the Legendre symbol of 2 over 17 squared. So that is where we're going to use this fact that the Legendre symbol is a group homomorphism. In order to take this thing, what kind of tricks can I do with it? Well, I could factor A if I needed to, and I know I'm allowed to split it up into these smaller pieces here. So what do I get? Legendre symbol of 12 over 17 is 12 a perfect square mod 17. It really reduces to asking, well, is 3 a perfect square mod 17? Which perhaps is maybe a little bit easier to check for. Who knows? We'll see some more tricks in a minute. Why did I just look at this one? Well, what's going on with the other factor? That's something squared. That thing's going to be 1, so I don't have to worry about it. So again, this symbol here really just depends on this one. Now, maybe it's not any easier. Like, all right, you still got to square every number 1 through 16 and see if you get 3. Is that really any harder than squaring every number 1 through 16 and seeing if you get 12? You got a point. I'm with you. What's another trick that makes the Legendre symbol maybe nice to work with? What can help? And this is where old 19-year-old Gauss in 1796 came up with the theorem on quadratic reciprocity. So here we go. What is the theorem of quadratic reciprocity? We're going to take two odd primes p and q and assume they're distinct. And what does this tell me? This tells me that the Legendre symbol of p over q is closely related to the Legendre symbol of q over p. In other words, that's that idea of reciprocity there. They should be related to each other when you flip them. That's a pretty easy way to think about that. But then in particular though, it's trying to say if p is a perfect square mod q, that should be related to the question is if q is a perfect square mod p. And all we need to figure out in the middle is I need to take minus 1 to the p minus 1 over 2 times q minus 1 over 2. And we don't, those exponents look gross, but if p and q are distinct odd primes, then I know that both of those exponents there are, or at least p minus 1 and q minus 1 are guaranteed to be divisible by 2. So like these aren't really like fractional exponents. That's what I want to say. And there are some special cases, like, okay, what if one of p and q is 2, right? That's not an odd prime. Well, down here it tells me how do I handle the case if I've got to deal with a Legendre symbol that has 2 in it. And this says that 2 is a perfect square mod p. It is a perfect square mod p if p is congruent to 1 or minus 1 mod 8. So think 1 or 7 mod 8. And it's not a perfect square mod p if p is congruent to 3 or minus 3 mod 8. So think about 3 or 5 mod 8. And what else over here? How do you compute the Legendre symbol of minus 1 over p? Again, think about minus 1. Think about that as it's the same thing as p minus 1 mod p. Anyway, how do you compute that quickly? It should just be minus 1 to the p minus 1 over 2 power. Now notice in the book, right, this is a really heavy theorem. It's super old. It's by Gauss, who's a very important guy. A lot of his importance comes from this fact here in number theory. But this is a very hard thing to actually prove. And so we will be blown away when we look at maybe one proof of how Gauss did this, and we'll skip his other proof of how we did it. What we're focused on now is just using it. How do we use this in computations? And that's what we're going to do going forward here. And you can read through example 4.1.8, which answers the question, is 69 a square mod 389? And, well, maybe just to talk through a little bit of it. So 69 mod 389, I'm going to factor the 69 as 3 times 23. I'm going to use the fact that the Legendre symbol is really a group homomorphism, which allows me to split it into these two pieces here. And now I claim that this first one's minus 1, and so is the second one, so it should be 1 overall. And I didn't claim it, the author did. And the author tries to fill in these details. So like, how do I know this is minus 1? Why is that fast? Here's where quadratic reciprocity comes into play. The Legendre symbol of 3 mod 389, what we're going to do is we're going to flip it. And there's some baggage that comes along when you flip it, right? You should still have minus 1 raised to the p minus 1. I'll say 3 is p, and I'll say 389 is q. So it still should be to the 388 over 2 times minus 1 to the 3 minus 1 over 2, so 2 over 2. But the point is, though, you can't really see that that's a 388 because it's tiny. Let me try one more time. 388 over 2. The point is, though, that both of those exponents are even, so there really is no minus 1 there in that case. Now, if you buy that, that is where we've used quadratic reciprocity. This is due to Gauss, this step right here. And now what we're going to do is just think about what are some things that I know about the Legendre symbol. Well, the Legendre symbol of 389 mod 3 should be the same as whatever 389 is equivalent to mod 3, which happens to be 2. So these are, in a nutshell, all the algebra tricks that we're going to use in order to compute some of these Legendre symbols. You're going to use the fact that it's homomorphism. You're going to use the fact that I have this thing called quadratic reciprocity. And the last thing that you're going to use again is that the Legendre symbol, it's easier to compute them as far as the equivalence classes mod p go. So that's how we get minus 1. And it's the same story for how the Legendre symbol of 23 mod 389 works as well, where this step from here to here is Gauss's quadratic reciprocity law. So what I want to do is just add maybe one page in where we do one more computation that's similar to that, where I'll talk you through what I'm thinking while we do it. And so I'm going to ask just a very similar question here, something like, what's the Legendre symbol of 48 mod 59? And how I'm going to do that is the same way. First thing you do is try to factor the top. So 48, I'm going to think about that as 2 to the 4th times 3. And that's over 59. And now I'm going to use some of my tricks. So if I want to split it, I'm really using the fact that this thing is a group homomorphism. So that'll be the Legendre symbol of 2 to the 4th over 59 times the Legendre symbol of 3 over 59. And I'll use the group homomorphism property again, which allows me to bring this exponent outside of all of that Legendre symbol, 2 to the 4th times the Legendre symbol of 3 mod 59. And this thing, think about that. That's 1 or minus 1 to the 4th power. That's going to give me 1 no matter which one of those two it is. So this should just be equal to whatever the Legendre symbol of 3 mod 59 is, since again, this is 1. Now, we're at a point where, all right, is 3 a perfect square mod 59? I mean, that's not any easier than answering this question if 48 is, right? But now is where we're going to use quadratic reciprocity. This should be equal to, I should be able to flip both of these, but there's some baggage that goes along with it. I need to take this kind of fudge factor, minus 1 to the p minus 1. So I'll think of that as 58 minus 1 over 2. I'm sorry, I already did minus 1. So 58 over 2 times, I'll use q as 3, so 2 over 2. I might have missaid which one's p and which one's q. Just use one of these at one point and the other one and the other one. Subtract one from the other one. All right, so what do I get here then? What would this be? This would be 29, I think. So I got minus 1 to the 29th power. That means that minus 1's sticking around. So I'm going to have the Legendre symbol of 59 mod 3 times this minus 1 still. Again, when you simplify this stuff, it should still come out to be minus 1. Now, how do you do the Legendre symbol of 59 mod 3? You're supposed to be happier when you get a smaller number in the denominator, because now I can just reduce this thing mod 3, which is 2. So this will be the Legendre symbol of 2 over 3 times minus 1. And now we're asking ourselves, this is much easier to figure out in my head. Is 2 a perfect square mod 3? Does 2 ever occur as a perfect square mod 3? And now, the only way we have to really do these Legendre symbols is, well, let's think about what are the squares mod 3. 1 squared is 1. 2 squared is 4, which is the same thing as 1. So the answer is no. 2 is not a perfect square mod 3. That means this symbol here is minus 1. So I get minus 1 times another minus 1 is positive 1. Therefore, what we can conclude is that the Legendre symbol of 48 mod 59 is 1. So yes, 48 is a perfect square mod 59.